Okay, well, let's go ahead and get started. Does anyone have any announcements before we dive into introducing our speaker? All right. Well, today we are extremely fortunate to have with us Sarah Gibson, who is a senior scientist at the High Altitude Observatory at the National Center for Atmospheric Research. Sarah is a success story of our own department. She did her bachelor's degree in physics here at Stanford, where she did an honors thesis with Phil Scher, he told me. I have Phil and Todd to thank for helping me to fill in some details of this introduction. And then Sarah went on to do her PhD in astrophysics at the University of Colorado. She spent time at NASA Goddard Space Flight Center and the Catholic University of America, and also at Cambridge, before joining the High Altitude Observatory, where she has held various leadership positions, including deputy director, interim director, and section head. Sarah Gibson is widely known for her science and was the recipient of the American Astronomical Society's Solar Physics Division Karen Harvey Prize in 2005. She's also extremely well known for her service, both her public outreach work and her substantive service to the community. So she has served as a scientific editor for the Astrophysical Journal and served on a number of different national and international committees. That includes time, I think actually currently as the vice president of the IAU Division E for the Sun and Heliosphere, and time as the Solar Physics Editorial Board, on the board. Sarah is also committed to education and public outreach and has done a number of talks, including with the American Association of Universities Women's Expanding Your Horizons Conference for middle school girls. And she participated in the NOVA episode on Secrets of the Sun. Sarah Gibson's research centers on solar drivers of the terrestrial environment. So everything from short-term space weather drivers to longer-term variations in the solar cycle. And I, for one, have been looking forward to this talk all quarter. I'm extremely excited to hear about all of the rich solar physics that Sarah will tell us about today. So with that, take it away.
Thank you. That's a nice introduction. Okay, let's see if I can get this switched on. All right, does everybody hear me? I don't know if I'm amplified. I don't know if it matters. And we're good on Zoom?
Yes.
Excellent. Okay. Thank you so much for inviting me. This is a real pleasure to come back here. And I had to start with a shout out to Wilcox Solar Observatory here at Stanford, because I was lucky, one of the few, if not the only undergraduate to get to live there, where I lived for over a year. And I'd have to wake up at dawn and go set up the telescopes and pray for morning fog so I could sleep in. But it was great. It was where I was first introduced to the sun's magnetic field. Every day I would call the Space Weather Center in Boulder, Colorado, and tell them the mean magnetic field of the sun for the day. So that's how I was introduced. And, you know, magnetic fields on the sun has gone through all of my career, because the fact of the matter is just about every amazing mystery in solar physics you can trace back to something to do with the magnetic field. And despite the amazing observations, the incredible complexity of observations that we get, and we still get, there are still mysteries that we just haven't solved. And so that's going to kind of be a focus for today. Let me close out this little X. Okay, so what do I mean by complexity? And is it going to let me move? There we go. This is an example. This is the sun showing an eruption. I'm going to be talking about coronal mass ejections, or CMEs. I'm also going to be talking about the prominence, which is at the core of the CME, and it's what you're seeing so spectacularly blasting out from the sun in this eruption, in this dark structure here. Now, I have taken as a kind of an inspiration for this talk, the novel from the 19th century, Flatland, because I want to ask the question of how we can get away from our perspective of a fundamental, something that appears two-dimensional, and we can only observe from the ecliptic near the sun's equator to something that is truly three-dimensional. So I don't know if you're familiar with the novella Flatland. It's a very cool book. I recommend it much. It's a story of a square who lives in Flatland, which is two-dimensional space. And he has this sequence of dreams. And the first time he goes to line land, which is one-dimensional. And he tries to explain the two dimensions to the lines, but of course it's completely over their head. And I think he gets in trouble, and so they don't believe him. So he goes back to his Flatland and he has another dream. And this time he's visited by a sphere. And the sphere has come from Spaceland in 3 dimensions. And she tries to get him to understand 3 dimensions by having him fly up and down and watching her cross-section change in size. And he gets it and he's amazed. And he goes back all prophetic to Flatland and he tries to explain it and he gets thrown in jail. So it doesn't end well. But I'm going to tweak it a little bit, of course. I'm going to be talking about not a romance, but a star of many dimensions. I'm going to be talking about going beyond Flatland, and I'm going to be assuming the authorship, which also is a little of a departure from the Flatland, which was a satire of Victorian norms, both social and gender roles. And so, in fact, the shapes, the men were all shapes, two-dimensional shapes, and the number of vertices told you what class they were. So the triangles were the worker class, and the more vertices you had, the higher class, so that the ultimate leader was a circle. The women, on the other hand, were one-dimensional line segments. But it's an interesting thing that the men were afraid of this because they lived in fear that they would encounter a woman head on, think that she was a point, and be skewered. It's true. Anyway, I digress. Let me get back to the point of the talk. I was asked to sort of review cool solar physics, modern solar physics, and I'm going to start by giving you a history of our evolving view and introduce the concept of some solar magnetic mysteries. In the second part of the talk, I'll do a deep dive into one of these areas, in particular, magnetic flux ropes, these 3D twisted structures that are fundamental building blocks of magnetohydrodynamics, and that are a mechanism for the energy storage and release that we see in all sorts of phenomena throughout the sun, and to be honest, throughout the universe. And then I'm going to go to that polar perspective, moving out of Flatland, and in particular talk about the view that this might give us on the sun's dynamo, and how we might learn something if we were able to go out of our ecliptic plane and look down on the sphere. So let me start with the history, and I'll start with the 5th graders' view of a sun. Very simple two-dimensional drawing of a sun, perhaps. Actually, most 5th graders these days are more sophisticated, so maybe it's a kindergartner's. This kind of view was very quickly moved away from as soon as we started to have observations, because the sun is not a perfect, simple sphere. In fact, this was something that was known by Chinese astronomers. There's written records back to the 4th century BC of sunspots. But when the telescope came in the 17th century, and we were able to see that the sunspots were rotating with the sun, this just changed everything. A lot of people think that Galileo was the first one to see the observe the sunspots through a telescope. He wasn't. There were others. I believe Scheiner beat him to it. But Scheiner thought that they were planets. The sunspots were planets orbiting very, very close to the sun. Galileo got it right and realized that there were tracers of the rotation of something which was basically fluid. And then in time, continuing to observe these sunspots, an interesting pattern appeared, the so-called butterfly diagram that's shown here. And you're looking at latitude versus time. And the idea that sunspots emerge at certain times at higher latitudes, and then they emerge more and more of them, and move to lower and lower latitude emergence. This particular diagram, this picture, is something I took with my cell phone, because this is the original. I took a picture of the original image, which was made by Annie Maunder and her husband Walter Maunder, and they actually drew it. There's a letter that goes with this picture. It was gifted to HAO, which is where I work. And there's a letter which describes how a week of going back and forth, reading out information and drawing little lines describing what latitudes the sunspots were at over these years. And that's how this was made, the original butterfly diagram. But of course, we've been observing for a long time now, and we can go back in time and see that there is this 11-year sunspot cycle that changes in amplitude but stays very close in terms of length over the course of centuries. And then when George Ellery Hale was able to use the Zeeman effect to measure the magnetic field in sunspots, we realized that what we were looking at was a magnetic cycle. And so this brings me now to my first set of magnetic mysteries. How does the sun create and sustain this cycling magnetic field? Why is the sun roughly, and not always exactly, 11 years? And what kind of star is the sun? And I mean that dynamically, and I'll get back to that in the last part of my talk. But all of these questions then drive the study of the sun's dynamo to try to explain how you could have this cyclic magnetic activity. And this is a picture of Gene Parker and a basic schematic to set up the idea that the problem to be solved for the solar dynamo is to transfer between the sun's poloidal, which is basically the dipolar, the north-south field, to the sun's toroidal, or east-west fields associated with those emerging sunspots. And the foundational theory, just realizing that this is essentially induction that we're talking about here, that if you have a dipolar field, and because the sun is fluid and rotating differentially more quickly at the equator than the pole, you can shear and amplify that poloidal magnetic field and turn it into toroidal magnetic field. But then going the other way, getting the toroidal magnetic field back to the poloidal magnetic field, Gene Parker's insight that the Coriolis force operating on the turbulent convection zone could then in turn transfer the toroidal field into the poloidal field was critical. And this then led to the models of possibilities for the cycling magnetic dynamo. We also were helped by observations of helioseismology, which looked at wave patterns at the sun's surface and from them deduced the flow structure of the deep interior. And from this, it became clear that that differential rotation, the fast, which here is red, equators, and the slower high latitudes, blue, was something that went deeper and then came to a halt at a shear layer at the bottom of the convection zone. So all of this became very important for building models of the solar dynamo. But there were other magnetic mysteries to learn as well. Probably the first thing that humans ever saw of the sun's magnetic fields was the sun's corona, its extended atmosphere, which is the crown of any solar eclipse. But as spectroscopy emerged in the 19th century, it became clear that something strange was going on. The sun was looking, the corona, the sun's atmosphere was looking green. And at first they thought it was a new element. They called it coronium. But fairly quickly it became clear that what they were actually looking at was a highly ionized iron ion, so iron 13. And the implication being that the corona was much hotter than the sun's surface. It was 1,000,000 degrees as opposed to about 6,000 degrees at the surface. And as we went into space and we were able to observe at short wavelengths, this became more and more clear and we could see the structure of the sun's corona. What you're looking at here in the middle is a Skylab picture in the soft X-ray. And here you can see the hot corona at 1,000,000 degrees. And here you're looking in through what are called coronal holes, where the magnetic field is open to the heliosphere and you're looking down on the cooler, it's dark because you're looking down on the cooler photosphere. And so of course, this is one of the classic solar magnetic mysteries. How is the corona heated to 1,000,000 degrees? Now, to a large extent, it was pretty clear that it had to do with magnetic fields, that somehow the magnetic energy was transferring and dissipating and forming this hot atmosphere. And we're back to Gene Parker, because Gene Parker's insight that when you have magnetic fields, current sheets will spontaneously form on multiple scales and form what are called nanoflares, releasing energy in little bits all throughout the corona, that this is one possible mechanism for heating the corona. But at the same time, we observe waves in the sun's atmosphere, indicating that there may be a component of the dispersion of the waves that then also contribute to the heating. So this is still an area of debate and one that is driving ongoing observations at ever higher spatial and temporal resolution. Now, the other thing that really kind of opened a window was being able to observe, and by going to space in particular, being able to observe 24/7, being able to observe all the time, because I'll tell you, because I've worked a lot with ground-based data, And the exciting coronal mass ejection will always happen when it's night. I mean, this is just the way of the world. But when you go to space and you can observe 24/7, you can see all of the CMEs. And this was amazing. And what you're looking at here is that prominence I mentioned earlier, erupting in the core of a CME. On the right, you're looking at the CME itself. And this is something that's often modeled as a magnetic flux rope, which is the second part of my talk. But there are a lot of magnetic mysteries associated with this. Like, what is the 3D magnetic structure of these CME, the thing that then blows up as a CME? How does the energy build up? And then what triggers its release in the coronal mass ejection? And then what happens when it leaves the sun and as it moves to the Earth? And I'll get back to that in the second part of the talk. But we've gotten a lot of insight from the stereo satellites, which have sent 2 spacecraft in front and behind the Earth, giving up to 3 views on structures, allowing information about their 3-dimensionality. At the moment, we have 2 views because we have one of the stereo spacecraft plus the Earth's view. And more recently, the solar orbiter satellite has moved closer. It's going to actually go within the orbit of Mercury. And it's also going to be the first mission to get away from the ecliptic plane and to move up to 30 degrees heliolatitude. So I'll talk a little bit more about that at the third part of my talk. But first, I want to go back to one of the truly classic magnetic mysteries, which is kind of the corollary to the coronal heating mystery, which is how the sun's, so what Gene Parker had the insight back in the 50s, I believe, that this kind of a hot corona could not exist without expanding outward in the form of a solar wind. And this was a radical idea and largely dismissed when he published this. But then a few years later, Mariner launched and observed it. And voila, we have our solar wind. So it's fitting, I think, it's definitely fitting that Parker's name was given to the Parker Solar Probe, which is the spacecraft which is now has launched and has been going closer than solar orbiter. It is has gotten as far as 15 solar radius within of the sun, and it will get within 10 solar radius of the sun by the time it's finished. And Parker was present at the launch. Sadly, he died in March of this year, but up until the end, he was actively engaged in the exciting results of Parker's Solar Probe. And there were a lot of exciting results. For example, this is actually not a Parker Solar Probe picture, but this is an image, coronagraph data of the solar wind. So there might be a CME in there, but honestly, it doesn't matter, because what's cool about this image, which has been this movie, which has been processed to show the structure, is just how clumpy the solar wind is. It's a riotous torrent of the outer corona. This is what Parker Solar Probe is flying into. And this is a really interesting region, because this is where the forces of magnetism and the solar wind are duking it out for dominance. It's the so-called Alphane zone. And the thing that we learn from this kind of observation, as well as ab initio models, is that the Alphane zone is not a smooth and simple place. It's likely to be frothy because it has clumps of material and all sorts of structure, including magnetic switchbacks, which is one of the discoveries of Parker Solar Probe. Well, it's something that has been seen further out, but very rarely. What they found when they got close in, so they're in at the youngest part of the solar wind where it hasn't been processed, was that these magnetic switchbacks, these spikes in velocity where the magnetic field flips direction, are quasi-ubiquitous, by which I mean they happen all the time in certain areas and then sometimes they don't. And the question of this, why this happens, is one that is not really known. There are a couple theories going on right now. The idea that you have closed magnetic field and open magnetic field reconnecting back at the sun and sending a kink out, which is weird because in the magnetically dominated lower part of the corona, you would expect it to straighten out, but it doesn't. And then there's other ideas that maybe there are magnetic flux ropes which form to stabilize the structure. So this is an area of active research. And so here are my magnetic mysteries. Sorry, did you have a question?
Does the clumpiness represent temperature fluctuations or density fluctuations, and how big are they?
Density. And I believe this occulting disk might be about, I'm not sure, a few solar radii.
A factor of 10 increases in density, or a factor of 2, or
not actually.
Scale from the low to high density regions.
I'm not actually sure off the top of my head. I would but I think it's significant. I mean, these have been processed, but it's there. And this is quite close into the sun that we're looking at right now. Sure. So the questions are, where and how does the solar wind dominate over the magnetic field, the Alfvén zone? What are the magnetic switchbacks observed by Parker Solar Probe? And here's one which I'm going to come back to later. Why is the polar magnetic field that we measure at the sun's surface, or try to measure, inconsistent with the magnetic field that you would measure in the solar wind with any kind of in situ satellite? And that brings me to the second part of my talk, because I mentioned flux. I mentioned flux ropes without explaining what I meant. So now I'm going to explain what I mean. What do I mean by a magnetic flux rope? Well, the definition which I will apply is basically anytime you have magnetic field that's wrapping around a central axis or axes. I showed two examples here. This is a single axis flux rope, which is basically something like a slinky where you have an axis and you're just winding around the magnetic field. On the right, I have a spheromac. Where you have two axes. One of them is essentially the donut and the other is the donut hole. And those two axes are the magnetic flux wraps around. The reason they're interesting, first of all, they give you topologically distinct magnetic subsystems, which can cause all sorts of dynamics. But the reason that I'm going to talk about them is because I'm going back to that magnetic mystery of what is the 3D magnetic structure of the solar eruption precursor. So the first question we can ask, and I'm going to kind of give a loose life cycle of what a flux rope might go through, is where do they come from? And what they represent are essentially a building block of magnetic helicity or twist. And so you may recognize this picture, which was earlier when I was talking about the solar dynamo. And I said that you can have a magnetic field, poloidal magnetic field created from toroidal field, and it can be caused by the buoyant rise of twisted magnetic field, which then emerge in the form of a dipolar active region or sunspot pair. And so what would that look like if we were trying to observe it? Well, the initial thoughts were, okay, we're trying to look at a twisted structure coming through the photosphere. So you need to look for the U-loops, the dips. And what would they look like? And over on the right, I've got a vector magnetogram, and the kind of mustard and yellow, I'm going to show that again, are showing you the up and down, and then you've got directional field. So this is an example of a magnetic observation that was fit, in this case, by a spheromac type magnetic field. So U-loops have been observed. In this case, you can also see the kind of brown structure, because if you have dipped magnetic field, you have support for the prominence, which is at the core of the CME, and which is cooler and denser than the surrounding corona. But this is a very idealized picture, the smooth emergence of this kind of magnetic structure. And it's a very legitimate question to ask, could you actually have flux rope emerging through the surface of the sun? Because the atmosphere of the sun is extremely sparse, but the photosphere is relatively dense. And so as the magnetic field emerges, and this is an example of a simulation, the mass all gets caught up in the dips and the structure gets fragmented and broken apart. However, the twist is hard to get rid of. So if even some of it comes out, what tends to happen is the magnetic structure reforms into a magnetic flux rope, a new magnetic flux rope with a new axis. And on the right, I have a simulation which shows this full process. I hope you can see it. On the top is the magnetic flux looking down on it. So blue and red are the up and down. In the middle, you're looking at the coronal structures of the emerging, here it comes. And then on the bottom is looking from the side. Okay, you can see the thing is starting to come up and it's been all sort of fragmented into all sorts of structures. But look, it's reformed into a coherent structure. And yeah, you can see the sort of the knot of it right here. And now, boom, after a little while, after a little bit of stability, it erupts like a CME. And so this is kind of the really interesting thing about magnetic flux ropes, is that at least in the simple kind of force-free approximation, they represent a minimum energy state for a given amount of magnetic helicity or twist. So the magnetic helicity is conserved and it tends to form this kind of structure. Now, I've been talking about the prominence. But I want to kind of move away from that just a little bit, because the prominence is the stuff that's sitting in the dips of that magnetic structure. But the magnetic structure itself is bigger. It's a volume, right? And so here's an example. And by the way, the prominence is usually what we call it when it's at the limb. And sometimes you may have heard people refer to it as a filament if it's on the disc, as it is in this picture right here. Sometimes they can be extremely extended. And when you see them at the limb, that same structure, you see this dark kind of cavity that surrounds it, sometimes simultaneously on both limbs. And so the cavity is a tunnel-like structure surrounding the prominence, which we can model as a magnetic flux rope, and which is interesting because it's more actually, it actually correlates better with the magnetic structure of the flux rope because it's the whole volume, this cavity, whereas the prominence is just tracing out the dips. I like to think of it as the prominence are the invisible man has walked through paint and he's walking along, and that's the prominence. But the whole volume of the invisible man is what the cavity is telling us about. And magnetic flux ropes can model both, and that's what this simulation on the bottom is showing you with synthetic observations. And cavities are nice for looking at in terms of coronal mass ejections because they tend to be seen with these high latitude, large scale structures, which have longer time scales and bigger spatial scales than some of the more dynamic active region eruptions. And so you can watch in slow motion how a structure narrows and rises slowly, and it has all this substructure, and it's going to repeat, and eventually it erupts. This movie that I have on the left actually takes place over about 48 or 24 hours, I think the movie takes place over. And so this brings us to the magnetic mystery that I had before, which is how does magnetic energy build up in the corona and what triggers its release in eruption? And the theory with the flux rope is that you have this magnetic structure that emerges or reforms or somehow finds a stable equilibrium in the corona. And the flux rope itself wants to expand outward, right? But there are overlying magnetic fields, the red field lines in the simulation on the right, that are the strapping force. They're keeping it down, and it finds this equilibrium. But eventually, something happens to break the equilibrium. And in this particular simulation, in this theory, the idea is that the flux rope itself starts to push up from below, and it gets high enough that it actually passes a limit for the torus instability, which is the m=0 mode instability, kink mode instability, where it just expands outward. And so the height of the flux rope is what triggers the eruption. So this is an ideal instability that could cause the CME, like the one on the left. Let me go to another magnetic mystery I mentioned. How do the CMEs evolve between the sun and the earth? So let me take a moment to describe what we're looking at here. This is sort of a patchwork of coronal and heliospheric observations. On the far right, you've got the lower corona. So it's one of those images I showed, like the CMEs, kind of stretched out, flattened out so that we can see it. Let me run it again. And then a CME takes off from down below. It moves through the solar corona, moves through the heliosphere. Here is the Earth. And when it hits the Earth, you're going to see the solar wind density pegged to the right. And so we have some information about what happens from sun to earth. But there are things we know are happening, but we've only caught a glimpse of. We expect that the CME, as it moves through the solar wind, is interacting with the solar wind. It's getting deflected. It's getting distorted. It might be getting rotated. It may be having reconnections, even changing its topology from something simple to something like a spheromac. All these things we can mostly guess at. We have a mission coming up, the PUNCH mission, and it's going to launch in 2025, which is going to get a much better view on this because it's going to observe from pole to pole and fill the gaps in between the corona and the heliosphere. Okay, but all that is plasma, right? I've been showing you these pictures of coronal plasma, white light, extreme ultraviolet emission, basically. What about the magnetic fields themselves? How can we measure the magnetic fields themselves? Well, there's one place we can measure them quite well in a flux rope, which is in a spacecraft with a magnetometer, just looking at the solar wind that passes by it. And this is an example of that. So that would include Parker Solar Probe, but also many, many spacecraft that have magnetometers at the Earth. So here's a flux rope coming out to the Earth, and it sees what is called a magnetic cloud, a rotation of the magnetic fields inside the CME measured in situ. Now, this, of course, has the enormous benefit that it's a true measurement of magnetism and showing the rotation in the magnetic field. But it has the drawback that it's a tiny point intersection with a gigantic structure. So you're getting a time series as one point passes or one part of the structure passes you. So where would we like to measure the magnetic fields in a flux rope? And of course, the answer is everywhere, but especially in the corona, because that's where the magnetic field magnetic energy is building up and leading to eruption. And this now is an opportunity to present an alternative to the flux rope torus instability kind of picture that I talked about, because there are other models that argue that the flux rope was not there from the beginning, but it was in fact created during the eruption by what's called breakout reconnection. In this case, it's important that you have a quadrupolar magnetic topology, two different lobes of magnetic field with a magnetic X point, a place where the magnetic field is zero, or an X line, really, it's a three-dimensional structure above it. Because then you can get reconnection, so before I was talking about the competition of the two forces, right? And in the torus instability flux rope, the flux rope itself reaches a point where it pushes up from a below. With the breakout model, you take the top off, and then the energy is allowed to go out. But the energy is generally stored much lower in the prominence itself and not in the volume of the cavity. And so this brings us to our solar magnetic mystery revisited. What is triggering the magnetic energy release and eruption? Because these are two very different ideas. One of them is that you have an ideal instability operating on a structure in the corona. And the other is that you have a reconnection in a very important place, which then allows the eruption to happen. And so why we want to measure the coronal magnetic field, of course, is to solve these mysteries. And this is just an example of what you might look for if you could measure the magnetic field in the corona. On the left is the model I just showed you, the idea that you have shear down in the prominence in a quadrupolar topology with a magnetic X point. And on the right is the one I showed before, that you have a magnetic flux rope in the corona, which then has an ideal instability. And now I'm going to go back and forth with these two simulations and what they predict in emission. And what you'll see is that they both have cavities, right? But if you could observe not just the plasma, but the magnetic field at the same time, you could distinguish between these models, because the flux rope model predicts the energy is all stored in the cavity, and the sheared arcade predicts that the energy is stored down in the prominence. And then you could ask the question about why and where the eruption happens. Okay, so at the moment, we don't have measurements of coronal magnetic field. We're going to be able to do amazing things with the DKIS telescope, which is a 4-meter telescope, because it turns out the sun is photon starved, which seems ironic, but it's true when it comes to circular polarized light, which is what you need in the corona. Remember, the corona is quite dim. It's the brightness of the full moon compared to the sun. So you need a very big telescope to be able to observe the corona magnetic field. The DKIS will be able to do it, but has a small field of view. The Cosmo telescope is another that's been proposed, which would be the full field of view with a 1.5-meter telescope. But until we have that, we really have become very dependent on the one place where we can observe the magnetic field on the sun quite well, which is at the photosphere. And this is an ecliptic view, and this is going to be important because we're getting into the last part of my talk. We can observe the magnetic field on the photosphere, and what you're looking at, this is actually, I think, a simulation, but it makes the point. Blue and red are the different polarities of magnetic field. So this is a boundary condition on these coronal structures that I've been talking about. That high latitude polar crown, you can actually see that there's this kind of neutral line between the blue and the red at the high latitudes that underlies a structure like this. So you can take this and you can do some sort of model to extrapolate. There are various problems with that. One of the main ones being that the simplest model is called a potential field model, which assumes there are no currents in the corona. But of course, the currents is what makes the corona interesting, because that's where the energization is, and that's what drives the eruptions. So that's one problem. But there's another problem, which is that you get very good measurements of the photospheric magnetic field within about 60 degrees of disk center. As you go further away, there are projection effects. There are center to limb effects. There are things which, if you're down here near the equator, the sun will rotate by and you'll be able to do better on those structures. although they might evolve in ways that matter. But at the poles, you're stuck. Because at the poles, if you're observing from Flatland, you can't get rid of the fact that this last pixel is an enormous amount of space. And you can't get rid of the fact that you're trying to understand a magnetic field, which is mostly radial, and you're looking perpendicular to it. And this is why, to solve this problem, there's been various ad hoc correction factors. We do get a glimpse of the poles because the Earth moves about 7 degrees up and down from the heliographic equator, right? So you can, at certain times of year, once a year, you can get a better peek into one pole and then 6 months later into the other pole. And this has helped build models of what the polar field might be. But this is still, 7 degrees is not a lot. And so there are actually quite a lot of differences between the magnetic fields predicted at the poles for different observatories. And I chose 2 ground-based observatories here. I could have chosen 2 space-based observatories and had a very similar kind of discrepancy. They've got the same color table. On the right, of course, is Wilcox Solar Observatory again. And it has one of the most, I will mention that Dibyendu Nandi, who I got the picture from of Wilcox at the beginning, he wrote to me when I asked if I could use it, and he said, oh yes, and he said it was a thrill to go to Wilcox because as a dynamo modeler, the solar polar fields that constrains, we've got measurements since the 70s, and we use Wilcox as our best and kind of canonical measure of the polar magnetic fields. But even so, Wilcox also doesn't know what's going on at the poles because we can't observe it from the ecliptic. And this leads to a magnetic mystery I mentioned earlier. Because we don't really know the solar polar magnetic strength or its structure, we don't know why the fields that we measure at the solar surface are inconsistent with what we measure in the solar wind. And so no matter what model you use, no matter which of those observatory correction factors you use, the very best possible agreement you get between the polar magnetic field and the strengths that are measured by spacecraft in the solar wind is a factor of 2 off. And so this is an example of what might be going on. There might be a top knot of magnetic field that we just can't see from the ecliptic. So on the left, we have an example. All of these, this is now a polar view, like pretending you're looking down at this simulation. And on the left, we have what you would get if you kind of processed it the normal way from our solar observations. On the right, there are additional magnetic fields, either clumpy or concentrated, added. The 2 on the right then allow you to be consistent with the heliospheric magnetic field. But until we actually fly above and look down, we won't know. So how will a polar field help? Well, it gives you unobstructed, unprojected measurements of the photospheric magnetic field, which is the lower boundary on the corona and heliosphere. And this is important both for the closed magnetic fields, those twisted flux ropes in the polar crown, the sources of the flux rope CMEs, getting that boundary right, and the open magnetic fields, the polar coronal holes, which are the sources of the solar wind and what is it lies behind this discrepancy with the open flux. And I'm fading back and forth because it's simulation. This is a simulation of both emission and the magnetic field and field lines. And you can see how this coronal hole, dark region, lines up. And that's another thing. When you're looking at just one side of the sun, you're only getting half of the boundary. And you have to wait for it to rotate, and it may change in the time it gets to rotate. If you could look down on it, you'd get a snapshot of that coronal hole boundary. Okay, but it's another kind of boundary. It's a lower boundary in the corona, but it's an upper boundary on the dynamo. And so what you get is an unobstructed, unprojected measurement of the photospheric fields and flows. So in terms of fields, I've already talked about the boundary and the importance of the polar fields, but there's also an importance of observing the evolution over time of the polar magnetic fields. Is the magnetic field that emerges in the sunspots, is it just sort of passively transported to the poles, and this is what cancels out and causes the magnetic field, the poloidal field? Or are there local sources and sinks at the poles? And we don't know because we don't observe there. And then in terms of flows, there are 2 mean axisymmetric flows that are fundamental to the dynamo. The first is the meridional circulation, the north-south flow, which we know from measurements, including helioseismology, is poleward at the surface. So it's often been referred to as a conveyor belt for flux at the surface of the sun. But that's at low to mid latitudes. And we have some information going deeper because helioseismology lets us go deeper. But we basically have no information here at the high latitudes. For all we know, there could be a countercell. So the magnetic field could be moving towards the poles, but then there could be a flow in the opposite direction and maybe a subduction. We don't know. The other mean axisymmetric flow is differential rotation, east-west. And I've mentioned that the flows are faster at the equator than the poles. But we don't know what's happening at the poles. Does it stay retrograde? Does it stay slower than the mid-latitudes? Or does it actually spin up in a polar vortex and go prograde at the poles? We don't know. And this matters for the solar dynamo modeling. Now, this is now the full picture of something I've been kind of showing bits of throughout the talk. Because for a solar dynamo model, as I've said, you have to have a means of going from poloidal to toroidal, from north-south to east-west and back again. And this is a schematic showing the whole process. In this case, you have rotation on a north-south field, which shears it and amplifies it, creating toroidal field from the poloidal field. It rises, moves through the surface, and here we have the poloidal field in the active region. And here's where that conveyor belt comes in, because it gets moved with a tilt to the sun, to the poles, and actually cancels out the magnetic field there, and then is subducted and transferred on a conveyor belt down near somewhere in the convection zone. It's not really known. And so this is a kind of ending up with basically a north-south field of the opposite direction at the beginning so that we can continue the magnetic cycle. But this is a very popular model because it answers a lot of questions. For example, that question of why is the solar cycle roughly 11 years? Well, the answer is the clock is set by the speed of that conveyor belt, that meridional circulation. But it makes a lot of assumptions, including the assumption that the magnetic field is essentially passively taken to the poles and brought down, and that there is no other source or sink of magnetic poloidal or toroidal field. And what kind of sources or sinks might there be? Well, there can be local processes happening in a distributed way throughout the convection zone, where you have helical fields, and you have, so in this case, we're looking at a little cartoon where you have north-south fields. So now we're looking at a smaller element, think of it as a cylindrical kind of convective cell. You have north-south field, and you have helical convection, which is transferring the north-south field to the east-west in a local way. And what's interesting is that the models that do this, the large simulations, numerical simulations that apply this kind of convection, have demonstrated that you can create global structures from this local process, basically. These wreaths of magnetism that can arise from these dispersed helical flows. And the same kind of process can happen in the other direction, going from toroidal to poloidal. And so this is a turbulent dynamo mechanism. And the question of whether this happens on the sun gets to that last magnetic mystery I mentioned, which is what kind of star is the sun, dynamically speaking? This is a sequence of stellar convective, these are different stars, global convection. And going from one extreme, from a non-rotating convective star on the left to something that's rotating so fast that actually convection is suppressed. We know that the sun is somewhere in the middle because we know that it's rotating and we know that convection is there. So we know it's somewhere in the middle, but we don't know exactly where. And this balance and this question of to what degree rotation is affecting the convection matters because it has impact onto the efficiency of those turbulent dynamo mechanisms that I was talking about. Which brings me to this, yes, and so then again, back to the poles. Why the poles are particularly useful is that if you have rotating convection, so it's not just like boiling water on a stove, but it's spinning around, so you have this kind of columnar structuring overall, then the pole gives you a really interesting view because you're looking down on the vertical motions as opposed to sideways, which is the view we get from the ecliptic. So it's a fundamentally different view, and it allows us to get a sense of the degree to which you have this kind of rotational dominance. And so I'm going to land on this. I think this is the last main slide. which is why do we want to go to the sun's poles? I asked the question about why we wanted the coronal magnetic fields, and it's the same reason. We want to solve magnetic mysteries. So that simulation I just showed you was for one example of what's called the Rossby number, which is the ratio of these flows, the convective speed and the rotational speed. And you can see that with increasing influence of rotation on convection, these vortical flows become smaller in spatial scale. And this is the view from the stellar pole. And what's interesting is that these flows, the ones I mentioned before, the meridional circulation and the differential rotation and this convection, they're coupled. So they don't operate independently, they operate together. And the simulations have given us some insight of what we might look for at the poles to distinguish between and to basically narrow down and pin down the dynamical regime of the sun. In particular, so we're going from bottom to top is more and more rotationally dominated, and the rotationally dominated is actually where the turbulent dynamo processes are more efficient, so they're likely to play a bigger role. The first thing is that if we look at the size of these spinning gyres, you can see they're changing, they're getting bigger with less rotational influence. Second, if we look at the differential rotation right at the poles, if we see, so red is the fast, this is now measured relative to kind of a mid-latitude. So red is prograde, so moving fast, and blue is retrograde, moving slow. If the sun is just gets slower and slower and slower, that's actually an indication based on these simulations that we're in a rotationally dominated regime. But if we actually see it spin up, that is a very strong indicator that the sun is right at that boundary of rotationally and convectively dominated flow, where the Rossby number is 1. And finally, I mentioned the countercell and meridional circulation, which is interesting for a lot of reasons. It could affect cycle length, it could affect, but it also is an indicator if we have a countercell that we have rotationally dominated flow. So these are flows that we could look for at the poles if we could go there. And finally, you know, I've talked about all these things we kind of expect to find, right, at the poles, because we've got simulations, we have questions that we want to answer, but there are also questions we don't even know yet. And that's been the theme throughout, that every time we've opened an observational window, a new magnetic mystery has appeared. And that's going to happen too if we go to the poles. Because as we know from flying, Cassini went to Saturn, Juno went to Jupiter, and the structure they found there is inspiring. Well, it's beautiful, but it's also just inspiring new assessments of what's going on and how we can use this unique view. Anytime you have a rotating structure like this, the view from the poles is fundamentally different than the view from the equator. And that's what these planetary observations really demonstrated, and I'm sure will be true for the sun as well. So here's my conclusions. The more we observe, the more mysteries are revealed. Magnetic flux ropes are a fascinating structure because they are vehicles for energy generation, storage, and release. Their appearance will change depending on what stage of their life cycle they're at, as well as what aspect of the flux rope is being observed. It's like the old story with the elephant and the 3 blind men, right? If you are observing a magnetic flux rope and all you're doing is just going in and touching it, sampling the information in situ, you'll get one piece of information. But if you're taking an image of it from one view, you'll get another piece of information. If you're looking in certain hot areas and cool areas, you'll see different things. And so putting it all together really drives us towards a unified 3-dimensional view of this magnetic structure. And then finally, I would argue that solar dynamo modeling is stuck in that it requires more information about the sun's dynamic regime. It's very possible that that Babcock-Layton mechanism is happening at the same time as these turbulent processes. But we don't know to what degree one or the other is operating until we know if the sun, what dynamical regime our sun lies in. And for that, we need a new vantage to get this, to solve this outstanding magnetic mystery. So thank you.
Very much for that excellent comprehensive talk. Okay.
I mean, like, I can ask you all these questions later too, but so my big one that I wanted to ask was, and maybe you don't necessarily have to opinion on this, but in terms of flux rope eruptions, presumably in different scenarios, both of the theories that you presented can occur on the sun. It's not one or the other.
Mhm.
But there are other theories in terms of eruptions and stuff too. Is there any signature that we could look for that would discount certain theories? Or is it basically like, well, we can just look for all of these things, proof that they all exist, and it's not, there is no one or the other, or it's the other or the other? Is there something that we could look for that we or not find that would discount?
Yes and no, but let me answer it in two ways. First of all, I have a sneaking suspicion that both mechanisms are operating on the sun, and that there may well be a spectrum going from the active region where there's flux emerging all the time. It's really dynamic. There's strong fields, and you have more complex topologies with the quadrupolar topology, and so you might never have enough sort of peace and quiet for a long-lived flux rope to form and survive. And so the breakout mechanism or other mechanisms may be the dominant mechanisms for the CMEs coming from those regions. Moving towards those polar crowns that I was looking at, they're large quiescent filaments, which basically build up over, that magnetic structure builds up over weeks or even months, where you get currents that grow and you have a stable equilibrium for a very long time, so that eventually the thing that drives it is not, activity nearby or a magnetic reconnection above, but is an ideal instability. So the yes part of it, so in that case, the answer is no, you may never distinguish that one is always true and one is not, or any of these models. But in the case of the cavity prominent CME, I think you can, because, and that's what I was showing, you have this kind of, if you find your magnetic field, that you have an axial magnetic field, a flux rope, if you looked at it in line of sight field, is going to have a bump in the middle where the axis is essentially. And if that is centered on the cavity, that's a strong indicator you have a stable flux rope. If, on the other hand, you have this cavity, but there's no strong field, it's maybe down below, and it maybe kind of sort of sticks its tongue out during the eruption in the slow rise phase, that's an indicator you have something more like this shear decade model. So I think we can rule out models in that particular simple slow-mo coronal cavity, high latitude type structure.
I can ask much less informed questions. But the polar mission, is the scale, should I be picturing something like stereo, except it's going over the pole of the sun? What's the kind of scale of this? And I can barely remember from my youth that Ulysses went over the poles of the sun, but I don't remember what instrument. Did it not even have a camera?
Right. So Ulysses, exactly. Ulysses used a Jupiter slingshot to go above the poles, and it detected the solar wind in situ, but it did not have remote sensing. There was actually supposed to be a US satellite to follow on and do the images. It didn't happen.
Put a camera on your spacecraft.
Yeah, well.
Did you know lesson?
Yes. And yeah, Doppler magnetogram. But the solar orbiter is going to go up to 30 degrees. And it may solve this heliospheric open flux mystery, because it may be able to peak enough into the top knot to kind of resolve it, but it may not. Some of these models, some of these possibilities are not, it's not high enough. For the Dynamo, the flows that I was talking about, it's not high enough. You have to get up to about 75 degrees and look down. And you need to be up there for a while. Probably, if you want to capture the time scales of the flux transport, you want to be up there for a few months. And the other issue is to do helioseismology, you have a signal to noise issue. And especially if you're going to the poles, you're probably going to be sending up a fairly small Doppler magnetogram, not a gigantic, huge, high resolution thing. So you're going to want to have enough time to beat down the noise and get a meaningful signal. And again, about 3 months, 75 degrees is sufficient to do that.
We don't understand why there's a differential rotation.
Well, that's a good question. And depending on this Rossby number, you can get different results, right? You can end up, there are stars, you can have solar rotation, which means it's doing like the sun and it's fast at the equator and slower at high latitudes, or you could have anti-solar rotation. And whether one happens or the other is a function of this, how convectively dominated or how much rotation is affecting it. But essentially, it's the rotating spherical fluid that's doing it in convective outer, at least the convective outer layer. Well, I mean, if you, I think it's this idea of, what is convection? And we're used to thinking about the boiling water on the stove. But if you had that boiling water in a spinning cylinder, you might start to get some sense of the processes involved in something like the sun or a star that's where the rotation is significant compared to the convection. So the insight we're getting really are from these large hydrodynamic even. You don't even have to do the full MHD simulations to start getting insight as to how the rotating spherical fluid is going to behave in a convective star.
We talked about possibly two types of eruptions. Active regions, very complex field, and maybe high latitude prominence eruption, maybe simpler configuration. But do we really understand the latter? People often talk about flares. Eruptions associated with big flares, but polar ground filament eruptions, people really understand the magnetic field origin of those things. And what I meant is, when people talk about the future, people talk about the coronal field measurement, but only at strong field regions. But what about weak field regions? Don't we have to characterize those regions better?
So the question is whether we are characterizing the weak field regions well enough to be able to talk about their eruption. Is that right, Naraki? So yeah, exactly, which is why we have to measure the coronal magnetic fields, especially when we don't even have boundary conditions very good because they're at high latitudes. But one of the most interesting research in this area is work by Duncan Mackay and Anthony Yates, who use surface flux transport. They put in those flows, the meridional circulation, the differential rotation, diffusion, and they show how when you merge active regions, they will eventually kind of go to high latitudes and coalesce into these flux ropes. And so they're using this data driven, right? They're using the observations, but then they're letting it evolve and demonstrating how you can build these structures. But the fact is we don't have observations right now of these structures, except for what we infer from the image of a cavity. But I just showed you two cavities with very different magnetic structures. So we don't know until we can observe the coronal magnetic field.
When you're trying to observe the poles and looking at, do you expect them to change over that 11-year cycle, over the solar cycle? And if so, how would you go about actually observing it long enough to get enough data for that full 11 years, or do it switch twice?
That is a great question. Not only do I think that they're going to change over the 11 years, I think they won't be the same from one solar cycle to another. There's very good reasons to believe that you might have a situation where you have a counter cell, so the meridional circulation coming back equatorward some cycles and not others, and that this might be why some cycles are longer than others. We won't know till we observe it, and as you say, you have to observe it over longer timescales. So I personally think the first thing we need to do is to go see, right? Go spend a few months up, get that discovery space. Pretty much everything I talked about you could do with sending a spacecraft up to one pole, maybe the other pole. But then we have to build the 4π. And we talked a little bit about this at the tea this morning. We have to get coverage because we need to be able to observe the full 4π of the sun from above, from behind, from the side. And so there are various ideas being proposed right now of constellations of spacecraft, maybe a diamond configuration or a configuration where you have like two going over the poles and then two going this way so that you have constant coverage, or maybe you put some in the stable Lagrange points, the L5, for example, the L3 is another. I mean, there's all these things, but there are questions about, there are things we have to address about making sure that the satellites can communicate, making sure we can get the data downloaded, making sure we can have systematic consistency between these different satellites and the instruments on them in order to build this picture. But I think that's the future. There's no question in my mind that in the end, the way we're going to solve these magnetic mysteries is to have essentially, I gotta think at some point we're gonna have a Dyson sphere, right? But I'll start with just a few satellites from the different vantages around the sun.
The concern is that sentinels going toward the pole and we wake up maybe 4 satellites
So I think the question was if you had sentinels between the sun-earth line, which also would be good to sample the different in situ. Oh, you're not even talking about that. You're just talking about like 4 satellites, 2 going over the poles and 2 on the, how much that would cost. I don't know, but a fair amount, I would think. I know that a single mission,
Not the right units.
I can give you the number I know, which is that you can do a single satellite to the poles, as was proposed by the Solaris mission at a mid-X price point, which is what, 250 million? Which, come on, astronomers, that's nothing. That's nothing. That's chump change, come on.
I mean, one way the landscape shifted is that high delta V launches are a lot cheaper than they were 10 or 20 years ago. You're not going to need to play these Jupiter games anymore.
Well, the Jupiter game definitely helps. And that's how like Solaris did it, was to get up there, because you have to be up there long enough. You have to stay up there. But you know, towards the future, who knows, maybe we will have solar sails capable of getting out of the ecliptic and not worrying about and not having the same orbital constraints. I think there's going to be a real need to go for miniaturization of instruments to make sure you can fit them on all of these. I think there's a need for a disaggregated approach so that NASA could send some satellites, maybe ESA could send some, JAXA could send some. I don't know, Elon Musk can send some. Maybe he has a reason. Maybe he can send a Buick or whatever it is, a Ferrari to the poles. But there may be multiple players here and opportunities to fill in this region. And the more we can drive towards the cheap measurements, light measurements, the more we can actually fill this space in, I think.
Seems like an excellent vision for the future to, and oh, should we have one last question? Go for it.
I have a shameless plug and the last question. So my shameless plug is that if this stuff is exciting to anybody at the spotlight is working on it. Stanford is leading a new science center driven to trying to answer some of these questions. We just got 5 years of funding for this, and we've got space and some money for some postdocs and some students. So if anyone's interested in working on any of these problems, come up to the Soul campus. And my last question is, if you had to explain your work to a 5th grader, what would you say that you do?
Okay, so first of all, I want to repeat your shameless plug because people online might not have heard it. And she was talking about the Coffees Drive Center, which is a major achievement by the group here to get that funding, 5 years, I think, and there's opportunity there for people who are interested in these problems, solving some of these mysteries. Second of all, I would show them the movies. What I would do is I would show them that, and I would say, look, this is our sun. This is happening right there. And look at this beautiful complexity. And you see that thing that blew up? Well, in 3 days, your cell phone's going out. So you want to know more? That's what I would do.
Fantastic. Thank you so much. All right, we have refreshments, the usual place. And, thank you.